All right, let's talk about something wild. Right now, inside all of us, there's a secret conversation happening. A really high-stakes, hidden alliance between three of the body's most powerful forces. And figuring out their secret language, well, that's one of the biggest and most exciting stories in modern medicine. So let's dive in.
So this is the central mystery, right? Think about it for a second. Blood clots, swelling from inflammation, and cancer. I mean, on the surface, they seem like they're from completely different biological worlds. A paper cut, a sprained ankle, a malignant tumor. What could they possibly have in common? Well, it turns out there's a deep, and sometimes dark, connection. What if I told you they're all part of the same secret club?
You know, for the longest time, medicine treated these processes like they were in totally separate departments. Coagulation, clotting, that was the emergency repair crew. Inflammation was the security detail. And they were filed in different cabinets studied by different specialists. But that was all wrong. The new reality, and this is a massive paradigm shift, is that these systems are constantly talking to each other. They're in constant crosstalk, and one can kick off the other, creating this incredibly powerful and often very dangerous feedback loop. Okay, to really get a handle on this, let's personify them. Let's meet the crew. First up, you've got coagulation. This is your impulsive first responder. It sees a problem, it plugs the hole. No questions asked, just pure action. Then you've got inflammation. Think of it as the overzealous security detail. It rushes to the scene, cordons everything off, but sometimes it gets a little carried away and causes a ton of collateral damage. And finally, the villain of our story, malignancy. This is the master manipulator, the rogue agent that learns how to hijack the first two for its own sinister agenda. So, how does this whole secret conversation get started? Well, every conspiracy needs a kickoff signal, right? In the body, that signal is often a molecule called tissue factor, or TF for short. You can literally think of it as the body's emergency flare gun. When TF goes up, everyone pays attention. It's the signal that gets this entire conversation started between our crew members. Now, with this flare gun, context is absolutely everything. Normally, tissue factor is kept under lock and key, hidden away inside the walls of our blood vessels. It only gets exposed when there's an actual physical injury, a tear in the vessel. And that's a good thing. But in disease states like cancer or a severe infection like sepsis, things go haywire. The bad guys, the cancer cells, the infected cells, they start plastering tissue factor all over their outer surfaces. The consequence? The entire body is put on high alert, primed and ready to form clots absolutely everywhere, even when there's no good reason to. Okay, so tissue factor fires the flare gun, but how does that message actually get received? How does a signal that says start clotting get translated into a command for an immune cell that says get angry and inflamed? The answer is just incredible. It's through these molecules called protease-activated receptors, or PARs. These are the secret handshake. This is the communication channel that lets the coagulation crew pass secret orders directly to the inflammation crew. So check out how this handshake actually works. It's both elegant and a little bit violent. First, a messenger molecule called a protease, which is basically a tiny pair of molecular scissors, shows up at the cell. Step 2, it literally snips off the very end of the PAR receptor. And here's the brilliant part. That new exposed tip is attached by a tether. It folds back on itself and plugs into a slot on its own receptor, like a key that was hidden there all along. That flips an internal switch called a G protein, which then shouts a brand new command, like release inflammatory molecules, deep into the cell's headquarters. Before we go any deeper, I just want to pause on this number to talk about the stakes. 215,000. That's the number of people who die from severe sepsis in the United States every single year. To really put that into perspective, that's more than deaths from heart attacks, lung cancer, and breast cancer combined. And this absolutely devastating toll is a direct result of this crosstalk between coagulation and inflammation going completely, catastrophically wrong. And this table really shows you why sepsis is such a nightmare. It is a death spiral. Just look at the first two columns. Increased coagulation and increased inflammation just feed each other. The infection triggers inflammation, which drives more clotting. The clotting creates thousands of tiny microclots that damage organs, which causes even more inflammation. And while this chaos is exploding, look at that third column, the body's own natural fighting systems. Its anticoagulants, they get completely used up. It's a vicious, self-amplifying cycle of destruction. Now let's bring cancer back into the picture, because this connection is a medical mystery that's over 150 years old.
Back in 1865, a brilliant physician named Armand Trousseau noticed this very strange pattern. Patients would show up with these weird, wandering blood clots, and then sure enough, months later, they'd be diagnosed with a hidden cancer. And then, in a truly heartbreaking twist, he developed the exact same symptoms himself and died from the stomach cancer he predicted. For a century, nobody knew why, but now we do. Cancer cells are the master manipulators. They hijack that exact same tissue factor PAR signaling pathway to not only cause clots, but to help themselves grow, invade, and spread.
And the real-world impact of this is just immense. This chart makes it crystal clear. A patient with cancer has a 4-fold increased risk of a dangerous blood clot compared to you or me. 4 times. Now, put that same patient on chemotherapy, and the risk just skyrockets to 8 times higher. This is a massive clinical problem, and it's rooted directly in this molecular crosstalk. So, okay, this all sounds pretty bleak, right? This deadly alliance seems unstoppable. But this is where scientists started to think like spies. They asked a brilliant question. What if we don't try to fight the network head-on? What if we could hack it from the inside? It was time to find a double agent.
And they found the perfect candidate. Activated protein C, or APC. This molecule is just amazing because it has a dual identity. It's one of our body's own natural anticoagulants. It's designed to keep clotting in check. But crucially, it also has these powerful anti-inflammatory effects. It was the perfect molecule to send in to disrupt the vicious cycle in diseases like sepsis. The excitement around this was huge. A massive clinical trial called the PROWESS trial gave a lab-made version of APC to patients with severe sepsis. And the results were stunning. I mean, look at this. You can see the death rate for the patients who got a placebo versus the ones who got APC. It reduced the relative risk of death by nearly 20%. For a disease as deadly as sepsis, this was a monumental breakthrough. It really looked like we had found a miracle drug.
But then reality hit. Once the drug was out in the real world, a dangerous side effect started to emerge. 1 in 66, that was the rate. For every 66 patients treated with this drug, 1 suffered a serious, life-threatening bleeding event. The very same property that made it a hero was also its fatal flaw. The drug had to be pulled from the market.
So this led to a really profound scientific puzzle. The drug worked, and it was deadly. How could a single molecule be both the hero of the story and the villain? The answer would take us deeper into the secret language of our cells than ever before, and it is fascinating. The answer lies in this amazing concept called agonist bias. It turns out that the outcome of that secret handshake depends entirely on how you shake. So on the left, you see what happens when the pro-clotting bad guy thrombin snips the receptor at one spot, arginine 41. It sends a pro-inflammatory damaging signal. But on the right, when our hero molecule, APC, snips the exact same receptor just a few amino acids down at arginine 46, it sends a completely different protective signal. Same receptor, totally different messages, all depending on where you make the cut.
And this discovery blew the doors open to a whole new frontier of medicine. The new goal became clear. Let's be smarter than the molecule. Let's get in the lab and actually engineer a better version of APC. The plan is to tweak its structure to dial down its dangerous anticoagulant activity while keeping or even boosting its amazing ability to send those protective signals. The dream is to create a therapy that gives us all of the benefits with none of the bleeding. And the potential uses for a drug like this are just breathtaking. We are not just talking about sepsis anymore. These next-generation engineered APC molecules are now being looked at for a whole range of devastating diseases that all share this common link of inflammation and vascular damage. We're talking about ischemic stroke, MS, inflammatory bowel disease, even things like diabetic kidney disease and radiation toxicity. Cracking this one code could have unbelievably broad implications for medicine. So if there's one core idea to take away from all this, it's summarized perfectly right here in this quote from the research. These systems are not separate. They are a deeply interconnected network. Inflammation and cancer push the body toward clotting, and the clotting signals, in turn, pour fuel on the inflammatory and malignant fires. They are completely and totally inseparable. Which leaves us with a final, fascinating question to think about. We're just beginning to learn how to eavesdrop on these secret conversations happening inside us every second. We're learning the grammar and the syntax of our own biology. So now that we're starting to decode this complex language, you just have to wonder, what other huge mysteries, what other complex diseases that have plagued us for centuries might we finally be able to solve?